Hello everyone, welcome to lecture 1. My name is Xiaodi, also go with Dennis. In this lecture, I will build this framework from the outside of the software system towards the inside of machine. This course begins with a mental model of programming. When people first meet programming, they usually see many unfamiliar words very quickly. Variables appears in the first page, then loops, functions, arrays, classes, databases, algorithms, and many other concepts follow. Each concept has its own definition. Yet the real challenge comes from understanding how all of them belong to the same system. So today I want to begin from a more fundamental question. What is the computer actually doing when software runs? At the most basic level, software receives the information, keeps that software, changes it according to the certain rules, and produces the result. That simple idea gives us a starting point for almost every topic that comes later. Programming languages help us press instructions. Provides working space, algorithms actionize the processing steps, databases keep information for long-term use. Front-end and back-end development divide the responsibility across a larger software system. Once these relationships become clear, programming starts to look much more structured. The goal today is understanding. By the end of this lecture, I want you to look at a piece of software and begin to see information moving behind the screen. Okay guys, let us begin with the way of programming is introduced. A beginner opens a textbook and sees something like int age equal. The teacher explains that is a variable. Later, a class introduces an if statement. Then a for loop appears, functions come after that. From a teaching perspective, this sequence is easy to organize because every chapter is a clear topic. From a learner's perspective, another question soon appears. Why does programming contain all of these things? Understanding a variable as a definition is very easy. Understanding its role inside an entire software system requires a large picture. Think about learning a language. A student may study nouns, verbs, tense, and sentences structure. This becomes much more useful when the student understands communication as a large purpose. Programming works in a similar way. Syntax gives us individual forms of expression. Software engineering gives those forms of a reason to exist. For example, a loop has value because computers often need to perform the same operation across many pieces of data. A function becomes useful when same logic appears in multiple parts of a program. A database becomes when information needs to remain available after a program finishes one session. So instead of treating each concept as an isolated item, we can place it inside a system. This is what I mean by building a cognition framework. The framework acts like a map. Once you have a map, every new topic becomes easier to locate. During the rest of lecture, we will build a map. Let us move away from programming syntax for a moment and look at a software experience. Imagine that you open DoorDash. You choose a restaurant and add a meal to your cart and enter in your address. You press button to place the order. From your perspective, the action feels very simple. Behind the screen, the system performs many operations. Your order contains several pieces of data. It may include the restaurant ID, the food items, the quantity, the delivery address, the price, and your account information. So the application first receives the information from your device. That information travels from interface to sphere. The sphere then applies rules. For example, it may check whether the restaurant is currently accepting orders. It may calculate delivery fees. It may verify payment methods. And the system may also estimate delivery time based on distance and current end. After those operations, the order becomes a structured record. That record needs long-term storage because you may close the application and open it again 20 minutes later. The restaurant needs to see the same order. The driver needs access the relevant delivery information. Customer support may need the record later. So data moves, storage, retrieval, and presentation. The same logic appears in many applications like Venmo. When you send money to a friend, the interface collects the payment amount and the recipient. The survey processes the transaction rules. The database records the result. Your account data retrieves the record. Amazon search follows another version of the same pattern. A user enters the keyword, the system processes the search, matching product data comes from storage. The front end presents the result. Once you begin to see software in this way, the graphical interface becomes only the web surface. Underneath that surface constantly moving through a structured process. Now we can move one level deeper. We understand that software processes information. The next question is how programmers describe those operations to a machine. This is where programming enters the picture. A modern computer ultimately works through electrical activity inside hardware. At the simplified level, we often represent those states using 0 and 1. Humans think at a much higher level. We think in ideas such as calculate the total price, find this customer, or show the latest message. A processor works through very small machine instructions. Programming language bridges this gap. At the lower end, machine code sits very close to hardware. Assembly language gives symbolic names to many machine-level operations. They introduce more abstraction while still giving programmers strong access to memory and system resources. Language such as Python and JavaScript move further toward human expression. Each layer reduces the amount of machine detail that a programmer handles directly. Let us take a simple example. Suppose we want to calculate the total price of 3 products. A high-level language may let us write something very compact. Total equals price 1 plus price 2 plus price 3. This single line looks simple to us. Inside the machine, many lower-level operations take place. The computer needs to locate values in memory, load them into processor registers, perform arithmetic, and store the result. The high-level language allows us to express the intention clearly, while lower layers handle the detailed implementation. This is an important idea because programming languages differ partly in how much detail they expose. It gives us programmer more directional. Python provides more built-in abstraction. JavaScript is closely connected with browser and web development. Every language represents a particular design choice. When you study a programming language, you are learning a suit for expressing logic in a form that can eventually reach the hardware. With that idea in place, syntax starts to become much easier to understand. Let us look at several common concepts through the lens of data. A variable gives a name to a value. Suppose an online store needs to remember the price of a product. We may write price equals 29.99. The word price becomes a convenient label. Later, the program can use that label in calculations. Arrays solve a different problem, and that the store has thousands of prices. Creating thousands of separate variables name would become difficult to manage. An array or another collection structure allows the program to group relative values. Decisions guide decisions. A store may give free shipping when the order value passes a certain threshold. The code can examine the order value and choose a correct shipping rule. Loops become useful when the same operation applies repeatedly. If a shopping cart contains 15 products, a loop can calculate the subtotal for every item. Functions package logic into reusable pieces. A payment calculation may appear in several parts of the application. Turning that logic into a function gives the software one reuse operation. Classes and objects later help us represent larger real-world entities. A customer has a name, an email address, an account status, and perhaps a purchase history. Instead of treating those values as unrelated variables, a program can group them into a structured object. The deeper idea here is simple. Syntax grows from the practical problems. Each construct is because programs face a certain type of information processing task. When you learn syntax through the perspective memory, it becomes much easier because every keyword has a purpose. Now we arrive at one of the central ideas in this lecture, memory. Software feels abstract because we see text on a screen. The software in a physical way. While the program runs, data occupies memory. We can imagine memory as a huge collection of numbered locations. Each location has an address. When your program creates a variable, the system reserves space for the value. Suppose we create an integer, int age equals 25, semicolon. The program needs enough memory to store the integer. The name age helps the program think about the value at the machine level. The value is in a specific area of the memory. This connection becomes especially valuable in C. C allows programmers to work with memory address through pointers. A pointer stores the location of another piece of data. Imagine a hotel. Every room has the room number. The guest is similar to the data. The room number is similar to the memory address. Pointer acts like a node containing the room number. With that node, the program can directly locate the corresponding data. This is one reason C has such a strong applicational value. It makes the relationship between memory easier to see. Memory management also introduces an responsibility. A program needs enough space to do its work. Large applications may handle millions of objects at the same time. Efficient memory use can affect speed, hardware cost, battery life, and scalability. This is where programming begins to connect with software engineering. A working program is one achievement. A program that handles resources efficiently represents a deeper level of engineering. Now, the difference between C and Python becomes easier to understand. These languages operate at different levels of abstraction. C gives programmers relative direct access to memory. Data type as explicit. Application may be handled manually. Pointers expose addressing. This means the programmer receives a high degree of control. That control is valuable in areas such as operating system, embedded systems, drivers, and performance-sensitive software. Python chooses a different balance. The language handles many memory details automatically. Its syntax is compact. Large libraries provide ready-made solutions for many common tasks. This makes Python very productive for data analysis, web services, automation, and artificial intelligence workflows. We can use a healthy analog. Manage a house during construction. The pipe or electrical cables are visible. The walls show their internal structure. This resembles C. You can see more of what is happening underneath. Now imagine a complete apartment. The electrical system works behind the walls. Water arrives through the faucet. The resident can focus on using the space. This resembles Python. The underlying complexity still exists, while the language handles a larger part of it for you. This comparison helps us understand the meaning of abstraction. Higher abstraction gives developer more convenience. Lower abstraction gives developer more direct control. Software engineering often involves choosing the right level of program. A microcontroller inside a washing machine may benefit from C. A data scientist analyzing millions of rows may prefer Python. The language becomes a tool selected according to the nature of the task. Let us now organize beginner C programming into a clear structure. Many textbooks contain chapters with titles such as variables, arrays, functions, structures, files, and pointers. Those chapter titles feel separate until we connect them to the movement of data. The first area is storage. A program needs a way to repeat information. Variables handle individual values. Arrays organize collections. Strings replace. Structures combine several related fields into one meaningful unit. Next area concerns during execution. Memory stores temporary working data. The information should remain available after the program closes. File operations provide one solution. The program can open a file, write information, read information later, and close a file properly. Then we have control flow. Conditions such as if and switch allow the program to choose different actions. Loops such as for and while let the machine repeat an operation. Functions create another layer of organization. A large program contains many pieces of logic. Functions allow developers to give names to those operations and code them whenever they are needed. Structures help represent more realistic objects. A university system may need to describe a student with several fields. Name, student ID, major, and grade can belong to one structured record. The final area in this map concerns direct memory work. Counters contain addresses. Malloc requests memory dynamically. Free release that memory when the program finishes using it. Once these 6 areas become visible, a C textbook starts to look like a coherent system. Every chapter addresses a different part of how information enters the program and moves through it. So far, we have looked mostly at programming inside one program. Now let us zoom out and look at complete software product. Consider Instagram. When you open the application, the first thing you experience is the interface. Images appears on the screen, button bound to your touches, text flap input, animation gives feedback. This area belongs mainly to the front end. The front end converts system data into something a human can see and interact with. When you press the like button, the front end captures your action and sends a request. The back end receives that request. This is where business rules enter the process. The sphere may check your identity. It may confirm which post received the action. It may update the like account and trigger another event. After the back end finishes its processing, the new state needs to be stored. Then the database handles that responsibility. The records users post comments like messages and many other forms of information. Later, another person may open same post. The application requests the data, the back end retrieves it from the database. The front end then displays the results. This gives us a useful model. Front end development focuses on users' interaction with data, and development focuses on system rules and processing. Database work focuses on persistent information and efficient retrieval. These areas belong to one continuous flow. Understanding that flow makes software architecture much easier to understand. Then move into the area where computer science becomes much deeper. A small amount of data allows many simple approaches. Suppose we have 10 students' records and want to find one student. We can inspect the records one by one. The operation finishes quickly because the dataset is tiny. Now imagine 10 million records. The choice of method becomes much more important. This is the domain of algorithms and data structures. A data structure determines how information is recognized. An algorithm determines how we operate on that information. Let us compare 2 ways of finding a value. The first method is linear search. We start at the beginning and check each item until we find the target. For 10,000 records, the worst case requires the 10 separations. Binary search works differently. The algorithm checks the middle item first. If the target is larger, the search continues in the upper half. If the target is smaller, search continues in the lower half. Every step reduces the search area dramatically. With the 10 sorted records, the target can usually be found in around 14 checks. This is a huge difference. The user sees the same feature, search for a record. The system experiences a very different computational cost. Data structure influences the results as well. An array offers storage. A hash table can provide extremely fast lookup for many types of key. A tree can support efficient search and ordered operations. This is why computer science spends so much time on algorithms and data structures. They determine how well software behaves when the amount of information grows. They alter small design choices into major engineering decisions. Okay, now we can connect programming with mathematics. Computers operate through discrete steps. The physical world often changes continuously. Consider a moving car. Its position changes through time. At one moment, we may want to know its speed. Calculus gives us mathematical language for describing this step of change. A derivative describes the rate of change. If position changes over time, the derivative gives us velocity. An integral focuses on accumulation. If we know velocity across the time interval, integration helps us calculate the total distance traveled. The idea of a limit becomes useful when we examine increasingly small intervals. Programming turns these mathematical ideas into numerical procedures, and that we want to calculate the area under a curve, like this. The curve may have an irregular shape. A computer can divide the area into many small rectangles. Each rectangle has a simple area calculation. The program adds these areas together. As rectangles become narrower, the approximation becomes more. This is a good example of how mathematics and algorithm meet. The mathematical model explains the relationship. The algorithm converts that relationship into executable steps. The program then presses those steps in code. This connection becomes very important in fields such as computer graphics, physics simulation, learning, signal processing, and quantitative finance. A computer can work with extremely complex real-world problems because mathematics gives some models and algorithms turn those models into operations. At this point, we can combine the major ideas from the lecture. Programming has several layers of understanding. Syntax sits at the visible layers. It gives us the vocabulary and grammar of a programming language. Algorithm sits one level deeper. They describe strategies for solving computational problems. Mathematics provides many of the principles behind those strategies. Software engineering then places everything inside practical constraints. A real system has limited memory. Servers has a financial cost. Users always expect fast responses. As the developers, we always need code that can be maintained over time. These constraints turn theoretical knowledge into engineering decisions. And building a recommendation system, the syntax allows you to write the program. Algorithms determine how recommendations are calculated. Ethics help define similarity, optimization, or statistical relationships. Engineering determines how the system serves millions of users within reasonable cost and response time. This also explains the structure of the computer summary. Programming languages are one part of the curriculum. Algorithms appears at another major area. Mathematics provides a foundation. Operating systems teach resource management. Databases focus on persistent information. Networks explain communication between machines. Software engineering connects technical work with large-scale project design. Once you understand this structure, the curriculum looks much more coherent. Each subject develops a different part of the same ability, creating systems that process information effectively. This framework also gives us a useful way to understand career development in software engineering. At an early stage, many technical rules focus on existing systems. Someone may fix small bugs, update configurations, support users, or make limited changes to a finished product. The developer works at a value. The developer may build a login feature, create an API, design a database table, or implement a user interface. With experience, engineers begin to make decisions that affect entire systems. An architect thinks about how servers communicate. Database design becomes part of the discussion. Traffic growth matters. Security requirements lose the structure. Cloud code becomes an engineering concern. At a deeper technical level, specialists may work on compiler design, database engines, distributed system, machine learning models, or operating systems. The key difference across these levels becomes from scope of responsibility. A junior engineer receives a clear defined task. A senior engineer spends more time deciding what correct technical approach should be. Architecture requires because several solutions may work. The strongest solution depends on cost, performance, maintainability, security, and future growth. AI changes this career structure as well. Code generation is becoming faster. Routine implementation becomes increasingly automated. As a result, engineers gain more value from systems and making high-quality decisions. The ability to explain why a design works become increasingly important. This is one reason I want to begin the course with a cognition framework. Your long-term growth depends on how deeply you understand the system behind the code. Okay, at final, let us bring everything together. Programming begins with information. User creates data through an action. Software receives the data and processes it according to the rules. Programming languages give developers a way to express the rules. Syntax provides practical tools for storing and transforming information. Memory gives the running programming a place to work. Front-end systems have software with users. Back-end systems handle logic and rules. Databases persist across time. Algorithms become important as the amount of data grows. Data structures determine how that information is organized. Mathematics gives us models for relationships, change, and optimization. Software engineering combines all of these under real constraints such as performance, cost, reliability, and scale. The central idea from today's lecture is very simple. Programming is much easier to understand when every concept to the way a machine handles information. When you encounter a new topic later in this course, try to ask yourself what role it plays inside this larger process. For example, when we study a variable, think about the storage. Like study a function, think about reusable processing logic, a database about information, an algorithm about efficiency at scale. That habit will help you develop a much stronger understanding of software engineering. The goal of this course is to build that understanding gradually. Thank you for joining me today.